Hey there, chemist. It's Dr. O'Malley here. I'm going to do a named reaction mechanism example for you. The one I've chosen is the Mitsunobu reaction. This was done by Oyo Mitsunobu in 1967. Let me start by showing you the overall transformation. It involves an alcohol. I'm going to use this chiral secondary alcohol as an example. And it reacts with triphenylphosphine, a special reagent known as diethyl azo dicarboxylate, which, yes, has the acronym DEAD, and a weak nucleophile. I'm going to use acetic acid as our example of a nucleophile, but there's a variety of nucleophiles that can do this. And you get a substitution reaction. You essentially turn the OH into a good leaving group, and in this example, you get an ester. So let's go through the mechanism and see how this works. The first part is the diethyl azo dicarboxylate, which looks like this. It's a nitrogen-nitrogen double bond flanked by two ethyl carboxylates. Reacts with triphenylphosphine. Triphenylphosphine is a nucleophilic source of phosphorus. It attacks one of the nitrogens. It almost looks like a conjugate addition you see there. And you form a zwitterion intermediate. So I will have a positive and negative charge in the same molecule, negative on that nitrogen, new nitrogen phosphorus bond with a positively charged phosphonium, and the rest of this is along for the ride. And this is an example of a betaine. This is a zwitterion, a species that has positive and negative charge in an overall neutral molecule that just happen to not be attached to adjacent atoms. That would be an ylide, if you remember the Wittig reaction. Then this sees our protic nucleophile, which is the acetic acid, and you do a very fast acid-base reaction. The nitrogen anion protonates, and you're actually going to spit out acetate in this case. So there's a lot of stuff that's along for the ride. And now we still have our phosphonium attached. I just turned it upside down, but it's the same thing. And a new hydrogen on that nitrogen. And here is the first time that the actual alcohol comes into play. So remember, way back in the beginning, I said I was going to show this with a chiral secondary alcohol. There it is. This will now, as a nucleophile, and pick up the phosphonium. All of this is just to deliver that phosphonium to the oxygen. So you get a new oxygen-phosphorus bond. Now in this case, I still have my hydrogen attached, so I now have a positively charged oxygen, and I have the rest of what used to be the dead molecule, which I'm going to draw right next to it. You can tell they're now single bonds. And there's an H on one nitrogen, and if you look back at the previous part, there is now a negative charge on that other nitrogen now. And that can do yet another acid base and simply take away the H of our original alcohol. So now I will get a byproduct. The byproduct will look like what's called a hydrazine. That's a nitrogen-nitrogen single bond. And the species that used to be our secondary alcohol now has this phosphonium attached. So everything we just saw there was all to deliver this phosphonium group onto what used to be just our alcohol. That was the whole point of this. And now we're actually almost done. Remember, not too long ago, we did an acid-base step back here where I formed a carboxylate. I didn't draw that, but it's been floating around this whole time. So I have a carboxylate, in this case acetate, and that's going to act as our nucleophile. It will attack the carbon attached to the oxygen, kick out the oxygen, and that's how you get your product. And hopefully you can tell from that arrow pushing that that one step right there explains why we have inversion of stereochemistry. I hope you're saying to yourself already, oh, that's an SN2. So this is a fancy SN2 reaction. The byproduct is triphenylphosphine oxide, just like we've seen in some of the other reactions. So overall, you get a pretty involved SN2 reaction. We can substitute alcohols, not good leaving groups, by turning them into good leaving groups with the Mitsunobu. And there's a variety of nucleophiles that do this. This is just one example where an acetate can do that and turn it into an ester. That's the Mitsunobu reaction. Thanks for watching.